So welcome to my new IB Chemistry with EAF YouTube channel, where I'm going to talk about structure 1.1 as well reactivity 1.1, which is also known as unit 1, which is the introduction of the particular nature of matter. Alright, let's begin. So everything is composed of matter, and matter is something which has mass and as well occupies space. And matter can be split into two different groups, into pure substances and mixtures, as we can see on the image on the left. And the pure substance is something which has a fixed composition as well properties, where on the other hand mixtures the mixtures are composed of two or more different substances that are physically mixed together, but they're not chemically joined. And as we can see, they're also being split into two different groups. The pure substances are split into elements and as well compounds, where an element cannot be broken more down and it consists of one type of atom, where on the other hand a compound is a substance composed of two or more different elements which are chemically bonded and as well have a fixed ratio. And the mixtures, they can also be split into, so there's the homogeneous mixture and the heterogeneous mixture. And the homogeneous mixture is a mixture where the components are evenly distributed and not easily distinguishable. For example, we have salt water in the sea. And the heterogeneous mixture is a mixture where the components are evenly distributed and can be easily distinguishable or distinguished. And as we can see in the image on the left, we have the heterogeneous mixture, where we have the pink at the top and the green at the bottom. So it's really easy to distinguish which one is pink and which one is green. And an example of that would be water and oil, where oil would be at the top and water at the bottom. And then on the other hand, we have the homogeneous mixture, where we can see it's evenly distributed and it's not easily distinguishable. An example would be the salt water, as I've already mentioned. And there are multiple different separating techniques for the different types of mixtures. To be exact, there's going to be 6. There's filtration, there's evaporation, distillation, centrifuge, paper chromatography, and as well recrystallization. And let's begin. So filtration is the separation of an insoluble solid from a liquid or solution, and with the help of the filtered paper, as the filtered paper is then used so that the water can pass through and the insoluble solids cannot. An example of that would be sand water. So as we can see on the image, we have a mixture with sand and water. As we pour the mixture down to the filtered paper, the solid, which is the sand, is going to be stuck, or basically it's being collected by the filtered paper, and the water can go through. And the sand is also known as a residue, where the water or the liquid or the solution is known as the filtrate. Other examples would be chalk and water. Another separating techniques would be evaporation, and it is when separating a mixture which has the solid dissolved in a solvent, which is usually water, and when heat is applied under the solute is being left behind as the water evaporates and the solute is left behind. An example of that would be seawater. So as we put seawater onto the evaporation dish, and as heat is applied, at one point the water is going to evaporate as it hits the boiling point, and what's left behind is going to be the salt. And this helps us to separate the solid, which would be the solute that is dissolved into the water. Another example would be distillation, and that is separating a liquid mixture based on the boiling points in the mixture. So an example would be when we're gonna have ethanol and water, they look the same, they look identical, but they both have different boiling points. And as heat is applied at the mixture, the one with a lower boiling point is gonna first evaporate and is being collected in another flask. And this helps us to separate the two different mixtures and the two different liquids. Another example would be the centrifuge, which is a common lab equipment where it spins a mixture at high speed using intense force to push the heavier components to the bottom while leaving the lighter ones at the top. And an example would be muddy water. So as the mixture is spinning, which will take a couple of seconds, the heavy ones are going to be pushed at the side, at the bottom of the tube, while the light ones are going to stay at the top. Another example of another separating technique is the paper chromatography, and it is when the mixture is to be separated by the chromatography paper, where it is then placed into a solution. So in this case, it's going to be water in the image, and the components moves up the paper and interacts with it because of the different solvation. As we can see in an example, we have black ink or an ink spot, and as time passes through, we see how the different colors shift up, and this helps us to separate the ink components. And lastly, one of the most terrifying ones are recrystallization, and it is when you have the impure mixture which is then dissolved into a small volume of hot solvent. Then the solution is then dissolved and as well evaporates with a lid, as we can see in the second image, and any insoluble impurities can be filtered at this stage. But the solution is also then has to be cooled, and from there on we can filter the crystals. An example of that would be purifying copper sulfate and as well purifying potassium nitrate. So now let's take a step away from the different separating techniques, and let's talk about the three different states of matter. So there's three common ones, which is solid, liquid, and gas. But there's also sometimes plasma, which would be above gas. So in the solid, the particles are packed tightly together, and they're held in a fixed position. And as we know, according to the kinetic energy, everything is in constant motion. So in a solid position, they start to vibrate. And on the other hand, the liquids, the particles are less close together, but they're not held in a fixed arrangement, and they take shape whatever the container is. For example, if it's a cup of water, they take the shape of the cup of water or from the box. But they still have a lot of space to move around. And lastly, we also have gas, which is where the particles are widely spaced and are more rapid and can move more rapidly around in all directions, and there's minimal force of attraction, so they are free and open. And then lastly, there's plasma, which is above gas, as I already mentioned, and this has a highly ionized gas state in which atoms have lost some of their electrons, which is something we don't see often. So those are the three different states of matter. As we can see, as we increase the temperature, we also increase the kinetic energy of particles. They become more free and are more able to move around. So as we can see, the solid ones are tightly packed together and they vibrate, where the liquid ones, they're still close, but they are not vibrating, but they can still move around a bit. And then gas is where we can clearly see they're widely spaced and they have much more space. And the shape and volume is also different for each. For example, in the solid, they have a fixed shape as due to the tightly packed, and as they're arranged, and the volume is already fixed. On the other hand, the liquids, they have a fixed shape, but the volume varies according to the container. And then for the gas, as gas is openly and can move openly rapidly around in all directions, it varies between the shape and as well the volume. But this also supports the kinetic energy. So the kinetic energy are the five kinetic energy are constant motion, small size, temperature, elastic collisions, and as well no attractions. So with constant motion, we mean that the particles are always moving and they change the direction when they collide. With the small size, we're talking about the particles are tiny, which leaves mostly space between them. Temperature is the higher the temperature makes, the particles start to move faster and collide as well faster. And elastic collisions is that during collisions, they don't lose energy, the motion continues. And lastly, for no attraction, the particles do not attract or repel each other. As we can see, we also have the heating curve, which can be explained in 5 different stages. So in stage 1, which would be from -50 to 0, in the solid particles, they are vibrating in a fixed position, as I already mentioned, and due to as kinetic energy is added, which causes the particles to vibrate even more, which increases the temperature, where we can see the rise going from -50 to 0. And as the temperature doesn't increase, instead kinetic energy is being used in order to rearrange the particles. The forces of attractions are overcome, allowing the particles to move from their fixed position to go into between other while in the same proximity. And as we can see, we're still right now at 0, but we're going to increase from 0 to 100 as the liquid particles are still moving around in an unfixed position. And as we as adding energy, it increases the speed of movement of particles, which increases as well the temperature, where we can clearly see the huge rapid increase from 0 to 100. And the temperature doesn't increase, instead kinetic energy is being used in order to rearrange the particles. Forces of attractions are overcome completely, allowing particles to move now completely independent of each other in all directions. And then lastly, as you can see at number 5, you can clearly see another increase from 100 to about 130. This is because in a gas, the particles are moving independently of each other, and adding energy increases the speed of movement, and temperature continues to increase accordingly. And as I already mentioned, as increasing the kinetic energy, the temperature as well is going to increase, and the particles are going to be much more widely, they have much more space. The change of solids are also important to know. As you can clearly see, the 3 different states can be put into 3 different, with the help of different processes, can put in different states. For example, from a solid to a liquid, it would require melting, or from a liquid to a solid, it would require freezing. And those are the common ones, where we have from a solid to a liquid, which is melting. From a solid to a gas is sublimation. Gas to solid is deposition. From a gas to a liquid, it's condensation. From a liquid to gas, it's evaporation. And from a liquid to a solid, it is freezing. So as we have talked about structure 1.1, which was talking about the kinetic energy, the different states of matter, and as well how they can be separated, the mixtures. Let's go to reactivity 1.1, which is where we're going to talk about open, closed, and isolated system. So a system is something where the chemicals that react, and the surroundings is everything else, which is often solution or the air. As we can see in an open system, the matter and energy can freely exchange, and as there is no lid on top, it can easily go and exchange itself. In a closed system, we can clearly see how a lid is being put on, and then the matter cannot be exchanged anymore, only energy, as the surrounding can take the energy away. And then in an isolated one, nothing can escape, because the energy cannot be exchanged with the surroundings, as it's being captured. And on top, the matter cannot be exchanged as well, as due to the lid on top. So to know that there's a difference between heat and as well temperature. So heat is a form of energy transfer that occurs between 2 substances due to the temperature difference, and it flows from a hotter substance usually to a colder one. And heat is either being absorbed, which is also known as an endothermic reaction, or it's being released, also known as an exothermic reaction. And which is important, it is measured in joules or calories. While on the other hand, temperature is a measure of average kinetic energy of particles, which are mostly atoms or molecules in a substance, and they're measured usually in Celsius or in Kelvin. So the heat and temperature, they are pretty much different to each other, which is important to know, because as I already mentioned, the heat plays an important role in endothermic and as well exothermic reactions. So an endothermic reaction is where heat energy is taken from the surroundings. So the surrounding, or the energy enters the system. So the temperature decreases from the surroundings as it takes in the energy from outside. So therefore, delta H is going to be positive, which is the change in heat. And there's going to be more energy for breaking bonds than released from bonds formed, and the products are being less stable than reactants, as you can clearly see in the image. So we have the activation energy, which shows us where the bond breaking happens, and we can see the energy absorbed. We can clearly see that delta H is positive compared to the exothermic, which I'm going to explain shortly. And then for the exothermic, we have heat energy, where the heat energy is released to the surroundings. So heat exits the system, as I already mentioned, and then the temperature increases in the surroundings. So therefore, delta H is going to be negative, and less energy for breaking bonds than released from the bonds are formed, and the products are more stable than reactants. So we can clearly see that in our graph. the activation energy goes much lower, and then as well the energy release is going to be negative. For delta H is going to be negative. And the commonly known examples for endothermic are going to be combustion and freezing, where on the other hand, for exothermic, we have melting and as well photosynthesis. So it's important to know what delta H is, which is the standard enthalpy change. And we can see delta means change in, and the H means heat energy. But also sometimes you will see a small circle on top, which has a line, which means standard conditions, which are usually at 25 degrees Celsius or 298 Kelvin. Also, they are at 1 atm, which is for pressure. And as delta H is negative, which means it's exothermic. And if delta H is positive, it means it's endothermic. Another what's also important is the enthalpy changes from temperature changes. So we have a formula book in our formula booklet. We have a formula which is known as Q equals mc delta T, where Q stands for heat exchange in joules, M stands for the mass of substances undergoing the reaction, C is the heat capacity of the calorimetry or water, and delta T is the change in temperature. And if we have water in our example, the specific heat capacity is going to be 4.18. And to calculate the change in temperature, you're going to take the final temperature measured minus the initial. Therefore, you will find the change in temperature. And delta H and Q are related. So we have to find delta H, you will have to do negative heat exchange in joules, which is going to be negative Q, over N, which is the number of moles. And that will give you the standard enthalpy change. To calculate moles, it is N equals mass over molar mass, which is important to know. Yeah. Thank you very much for listening. I hope you enjoyed the video. Have a nice evening.